So in this lesson, we're going to talk about some strategies for testing convergence of series. So we've learned a lot of different tests, and we also have some known series we can take advantage of. The first, of course, is the geometric series. If we recognize a geometric-looking series, we will then determine its convergence based on the common ratio if the absolute value of r is less than 1 or if it's greater than or equal to 1. Another one is called a p-series, if you remember, that looks like this. Where p is that exponent. And again, the p-series will converge if p is greater than 1, and of course diverge if p is less than or equal to 1. And then we have this other one called the alternating harmonic series, which is an alternating series with that n in the denominator. That one converges. And related to that, the harmonic series, which doesn't alternate, diverges. It's a special case, the harmonic series is a special case of the p-series when p equals 1. So here's a summary again of the tests that we've learned. The first is the test for divergence, and you look at the individual terms, and if the individual terms do not go to 0 as a limit, then the series diverges, and that's all you have to do. However, just because the limit does go to 0 does not guarantee that the series is going to converge. This test for divergence can only guarantee divergence if the limit does not go to 0. Then we have two comparison tests, the regular comparison test and the limit comparison test. And they both are set up in a very similar way. You have your series, which I'm going to call sigma of an, and you create another series, sigma of bn, that looks a lot like sigma of an, but focuses only on the terms with the most impact as n goes to infinity. So the highest exponent terms, or in the numerator, and again the highest exponent in the denominator, or throwing away plus a constant or things like that. And then you compare the individual terms of an and bn either with an inequality or with a limit of the ratio of an and bn. And then based on what happens there, you can possibly make conclusions about if you can determine convergence of the sigma of bn, you can then maybe determine convergence of sigma of an. Of course, these will only work for a series of positive terms. Then there's the integral test, which again is about series of positive terms. And if you look at the formula for the series and it looks a lot like a function you know how to integrate, then what you do is you create a continuous function that you can integrate, and you do the integral of that function, and depending on whether that integral converges or not, you've got the series converging in the same way, so either converging or diverging. The integral test is also good for error estimation. So if you want to approximate the sum of a convergent series, one way you can do that is of course, to truncate, which is always what you're going to have to do to approximate. You truncate, and then you use the integral test to determine an upper bound on the error using the integral from k to infinity if you truncate it after k terms. Again, the alternating series test. So again, there are three prerequisites for the alternating series test. It has to be strictly alternating. The individual terms in absolute value are decreasing, so absolute value of an plus 1 is less than absolute value of an, and also the limit of the terms is equal to 0, just so that you don't have the test for divergence creating problems. And there's also a way to approximate or estimate the sum of an alternating series by just truncating again, and then looking at the term right after you truncated, so the k plus 1th term, and using the absolute value of that as the upper bound on the error you might have. Then you have the ratio test, and that one, usually we're going to use the ratio test if you see a factorial or an exponential. If it's strictly exponential, you might just do the geometric series, but if there's an exponential with something else in it, or if there's a factorial, then the ratio test makes the most sense. And again, that's where you do the limit of the an plus 1 over an terms in absolute value, and if that is equal to 1, or if that is less than 1, you get convergent series. If that's equal to 1, it's inconclusive. If that's greater than 1, the series diverges. So be careful with the equal to 1 in that scenario. And there's another test which I have not taught you, but it's very similar to the ratio test. I'm just going to mention it. There aren't any practice problems about it, but it's worth knowing, which is where you take the nth root of the absolute value of a sub n. And if that limit is less than 1, then the series converges. If it's equal to 1, then it's inconclusive. Greater than 1, the series diverges. And again, that's similar to the ratio test in terms of these three options. This will be a something to the n type scenario, and the nth root will cancel the n. It won't be an x, though. It'll be something rather complicated to the n. And then you want to try to get rid of the exponential and just focus on the stuff that's that thing on the inside that may have been complicated for a series. So this is a quick summary. Now I'm going to do some examples without prompting what test we're going to use. We're going to come up with some conclusions about what might be the best approach. So here's our first example. We want to test the convergence of the sum as n goes from 1 to infinity of n minus 1 over 2n plus 1. The first thing I notice is that if I look at the individual terms, there's an n in the numerator and n in the denominator. That limit may not go to 0. So I'm going to start by taking the limit as n approaches infinity of the n minus 1 over 2n plus 1, just the individual terms of that series. And of course, the way to do that limit is to multiply by 1 over n. That's our limit trick that we learned. So it becomes 1 minus 1 over n over 2 plus 1 over n when I distribute 1 over n into the numerator and the denominator. And of course, as n goes to infinity, this turns to 0, this turns to 0. So it's 1 minus 0 over 2 plus 0, which is 1/2, which is not equal to 0. So by the test for divergence, we know the sum as n goes from 1 to infinity, the series that we were looking at, diverges. So it's always worth, especially if you can do it in your head, just checking to see if the individual terms are going to have a limit of 0 or not. Because if it doesn't, it's a trivial question. If it does, of course, you don't get any useful information yet, but at least you know that you can eliminate the obvious diverging series that way. Okay. So here's another one. Again, I'm going to look at the individual terms here. Now I notice that there's an n cubed here. There's also an n cubed here. So it's kind of like the one before, but that's a square root of n cubed. So when I do the trick where if I'm doing the limit of the individual term, and I do the trick where I multiply by 1 over n cubed on the top and 1 over n cubed on the bottom, it becomes square root 1 over n to the 6th on the top. So that actually does allow you to get 0 in the numerator. So the test for divergence is not going to work. So I got to come up with an alternate method. And I notice here that I've got a bunch of terms in the numerator, a bunch of terms in the denominator, and that this term here from the numerator and this term here from the denominator contribute the most when I make the limit go to infinity. This one doesn't do much at all. This one does contribute, but not as much as this one. So I'm going to do the comparison test, or potentially the limit comparison test. So I'm going to first set up, I'm going to let an equal square root of n cubed plus 1 over 3n cubed plus 4n squared plus 2, and bn equal, and I'm just going to take the terms that have the most impact as n goes to infinity, so squared n cubed over 3n cubed. And if I simplify that, I get, I'm going to do the quick and dirty thing. It's 1 over 3n to the 3 halves, because the numerator is n to the 3 halves. The denominator is n cubed. Subtract the exponent, you get n to the negative 3 halves, put it back in the denominator. So that's the simplification of bn. And now I'm going to do an inequality check, and I notice that something's going to go wrong. Remember, well, okay, before I do that, let's just focus on the convergence. So if I do sigma as n goes from 1 to infinity of bn, that's sigma n goes from 1 to infinity of 1 over 3, and then I'm going to do times 1 over n to the 3 halves. Well, the 1 over 3 is a coefficient that can get factored out, but this, you'll notice, is a p-series, p greater than 1. So sigma of bn converges. Okay, so since sigma of Bn converges, we're hoping to be able to show that sigma of An converges. So if I want to do a regular comparison test, I would want the An individual terms to be smaller than the Bn individual terms. And the An denominator is definitely larger than the Bn denominator because of these extra, if I look at this unsimplified version, these extra terms here don't exist here. But the An numerator is also bigger than the Bn numerator. So I can't make the argument that the An whole expression is smaller than the Bn whole expression. So the regular comparison test doesn't work, but I can still do the limit comparison test. So let's do the limit as n approaches infinity of An over Bn, the individual terms, become the limit as n approaches infinity of square root n cubed plus 1 over 3n cubed plus 4n squared plus 2 all over the 1 over 3n 3 halves. And of course I'm going to do the thing where I take the denominator and I flip it and make a multiplication problem. So it's really the limit as n approaches infinity of the square root of n cubed plus 1 over 3n cubed plus 4n squared plus 2 times 3n to the 3 halves over 1. So if I distribute this 3n to the 3 halves, let's actually factor out the 3. I'm just going to pull this 3 out to the front, and then n to the 3 halves is already a square root there, so it's just going to distribute n cubed into the square root. So I'm going to end up with the limit as n goes to infinity of 3 square root of n to the 6th plus n cubed over 3n to the 3 plus 4n squared plus 2. And now what I can do is I can multiply the top and bottom by 1 over n cubed, which on the inside of the square root will be 1 over n to the 6th. So when I do that, I get limit as n goes to infinity of 3 square root of 1 plus n cubed over n to the 6th, so n 1 over n cubed, over 3 plus 4 over n plus 2 over n cubed. And now as I consider n going to infinity, this will go to 0, this will go to 0, this will go to 0. So it's 3 times root 1 divided by 3, which is just 1, which is a positive real number. So because it's a positive real number, the limit comparison test says that the convergence of sigma of Bn will be the same as the convergence of sigma of An. So by the limit comparison test, sigma n equal to 1 to infinity of the original series that also converges because the Bn series also converged. Okay, so I look at this one again and I think about, what would happen if I did the limit of just the individual terms, but e to the negative n squared, remember, just means divide by e to the n squared. So I've got n over e to the n squared. That would end up being a L'Hopital's rule type scenario. I'm not going to mess with it. I know that one's going to have a limit of 0, but I'm not going to stress over it too much. So the question is, what method should I use? So the comparison test is kind of hard because I'm not sure what I would compare it to. If I change this into n over e to the n squared, well, both the numerator and the denominator have terms that are meaningful in terms of the limit as n goes to infinity. So I'm not going to do the comparison test or the limit comparison test. But I do recognize in this scenario that if I made that x e to the negative x squared, I know how to integrate that because I can use u substitution. So that would be one approach. Another approach, by the way, is because this is exponential, you could try the ratio test. I'm going to go with the integral test, but the ratio test actually also works. So I'm going to let f of x, you have to create a continuous function, equals x e to the negative x squared, so that a sub n equals f of n. Okay, so I'm creating a function that matches the individual terms of the series, and therefore, when I do the integral of that as n goes to infinity, I will get the same convergence on that integral as I will for the series based on the integral test. So now I'm going to integrate, and I can start anywhere, but I'm going to go from 1 to infinity. I'm going to be safe going from 1 to infinity, of x e to the negative x squared dx. Well, that's equal to the limit as b goes to infinity of the integral from 1 to b of x e to the negative x squared dx. So now, when I integrate this, I could do the u substitution, but I don't really have to, because I know that the negative x squared is the piece from the chain rule, it's the box, and the derivative of negative x squared is negative 2x. So the x part is there, what's not there is the negative 2, so I compensate by multiplying by negative 1/2. That'll cancel out the negative 2 that I'm going to get by using the chain rule in reverse. So this is going to be the limit as b goes to infinity of negative 1/2 e to the negative x squared. And again, if you want to take the derivative of this expression, you would get the x e to the negative x squared back. Now, of course, I shouldn't forget that I'm evaluating between 1 and b. So this now becomes the limit as b goes to infinity of negative 1/2 e to the negative b squared plus 1/2 e to the negative 1 squared, or equal e to the negative 1. Now, of course, this is a constant here, so I got to focus on this one. This is going to be the limit as b goes to infinity. I'm going to write that as negative 1 over 2e to the b squared, and then plus 1 over 2e. And you'll notice again that here, if I let b go to infinity, e to the b squared is going to go to infinity, and that's going to turn into 0. This is 1 over 2e. So the integral from 1 to infinity of x e to the negative x squared dx converges. And so by the integral test, I know now that the series converges. And that was what we were trying to do. Okay, here's another one. Obviously I can do a quick check on the limit. So if I try to take the limit of that, the individual terms, to see if it equals 0, I'll notice that this numerator has a lower exponent than that one. So this denominator is going to win out when I do the multiply by 1 over n to the 4th. And this limit will be 0. So I don't have to worry about the test for divergence, but it's always good to check. I recognize here very quickly this is an alternating series. So maybe I should just do the alternating series test. In fact, none of the other tests really do much good. The ratio test does work because you're doing the absolute value. The ratio involves the absolute value of a sub n plus 1 over a sub n. So that negative 1 to the n would disappear, but I'm not going to do the ratio test. I'm just going to do the alternating series test. So the series strictly alternates. So now let's compare, let's just very quickly do the limit as n goes to, I'm going to do it in reverse order here. The limit as n goes to infinity of a sub n is just the limit as n goes to infinity of negative 1 to the n cubed over n to the 4th plus 1, which is the limit as n goes to infinity of negative 1 to the n times, I'm multiplied top and bottom by 1 over n to the 4th, so 1 over n over 1 plus 1 over n to the 4th. And so the numerator is going to go to 0, whereas the denominator is going to go to 1 plus 0. So this limit is 0. So that's the second requirement for the alternating series test. The last thing I need to do is and I look at the absolute value of a sub n plus 1, which again, that gets rid of the negative 1 to the n part. So it's n plus 1 cubed over n plus 1 to the 4th plus 1. And then the absolute value of a sub n is n cubed over n to the fourth plus 1. So I want to be able to make a comparison between this expression here and this expression here. My hope is that this is smaller than this. Now we're kind of in trouble here because we're making this numerator rather bigger than this numerator, and this denominator bigger than this denominator. So it's hard to make the argument that this is smaller than this because the numerator and denominator are both bigger than their corresponding term over on the other side. However, I can make the following equivalent argument here. I can say, if I let f of x equal x cubed over x to the fourth plus 1, so that f of n equals the absolute value of a sub n, right? So I'm basically creating a function that follows the absolute value of a sub n. If I can show that that function decreases, then I've shown that this term here has to be less than this term here because that's what it means for a function to decrease. Obviously, we're talking about positive terms here, so the positive part is taken care of. So that to show that the function decreases, I'm going to take its derivative, so f prime of x, and I can use the quotient rule here, is 3x squared times x to the fourth plus 1, and then minus, and then derivative of the denominator is 4x cubed, and then times my x cubed left alone, all over x to the fourth plus 1 squared. And if I simplify that numerator, I'm going to get 3x squared times x to the fourth, which is 3x to the sixth, minus 4x to the sixth, so that's negative x to the sixth, and then plus 3x squared over x to the fourth plus 1 squared. And now I'm going to set this equal to 0 to make my comparison for my number line, for my chart. And I can factor out an x squared in the numerator. So I'm basically saying x squared times, 3 minus x to the fourth, or negative x fourth plus 3, over x to the fourth plus 1 squared. That's equal to 0. So basically this means that x equals 0, or x equals plus or minus the fourth root of 3. So what I've got now is I've got my values where the derivative is equal to 0, and then I can do my number line to determine where the derivative is negative, which would mean that the function is decreasing. I'm going to need another page in order to make this work. So here's the information from the previous page. I'm going to draw my number line. I'm going to label it f prime of x. I'm going to put my 3 zeros on there, negative 4th root of 3, 0, 4th root of 3. And if you think about it, remember x is just a stand-in for n, and I'm interested in what happens as n gets large. So the region I care about is this one. I don't really care about any of the rest of it. So I'm just going to pick a number that's in this region, something greater than the 4th root of 3. Let's pick 2, and what I'm going to do is plug 2 into the derivative here. So when I plug in 2 here, I get a positive number. 3 minus 2 to the fourth is a negative number. When I plug 2 in here, it's another positive number. So basically, I've decided that this entire region is negative, which means I can say that for x greater than the 4th root of 3, f prime of x is less than 0. So f of x is decreasing. Therefore, absolute value of a sub n is decreasing, because that's what f of x was a stand-in for, which of course then means that absolute value of a sub n plus 1 is less than absolute value of a sub n for all n greater than the 4th root of 3. Right? So, all right, so it may not happen at n equals 1, but that's not important. What happens is what we care about is what happens toward the end. So going back to the problem, we were trying to determine if the alternating series converged, and we showed that the limit was 0, that it was strictly alternating, and that the final thing, which is this inequality, holds true. So by the alternating series test, the original series, which was negative 1 to the n cubed over n to the fourth plus 1, converges. Okay, here's another example. I look at this, and as soon as I see that n factorial, I'm like, okay, this is going to require the ratio test, and of course I also have 2 to the n, so that confirms it. So I'm going to set up the ratio test. So I'm going to go with the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n. And let's see what that does. So that'd be the limit as n goes to infinity of 2 to the n plus 1 over n plus 1 factorial divided by 2 to the n over n factorial, which when I do my reciprocal of the denominator, limit as n goes to infinity of, again, the absolute value is irrelevant here because all these terms are positive, so I dropped the absolute value. So it becomes 2 to the n plus 1 over n plus 1 factorial times n factorial over 2 to the n. And now if I look at the n factorial and n plus 1 factorial, it almost all cancels, just leaving an n plus 1 in the denominator. And when I do 2 to the n plus 1 divided by 2 to the n, and I subtract the exponents, I get 2 to the 1 in the numerator. So this becomes the limit as n approaches infinity of 2 over n plus 1, which of course that limit is going to go to 0 because the denominator has an n in it. So what I've discovered then is because this number is less than 1, by the ratio test, so technically the ratio test says that sigma n equals 1 to infinity of 2 to the n over n factorial absolutely converges, but of course if a series absolutely converges, then it straightforward converges, so therefore it converges. But technically there's a little more information in the ratio test than just whether the series converges or not. All right, here's another one. Again, I look at this and I say, well, can I do a limit going to 0? Yep, the limit will go to 0. This kind of looks like a geometric. I don't think the ratio test is going to work because that plus 2, but this does look kind of geometric with that extra plus 2. So let's just do some kind of a comparison, either regular comparison or limit comparison. So let a sub n equals 1 over 2 plus 3 to the n, and b sub n equal, let's just throw away the plus 2, 1 over 3 to the n. Now I'm going to look at the convergence of that sigma of 1 over 3 to the n. So sigma as n goes from 1 to infinity of bn is sigma n goes from 1 to infinity of 1 over 3 to the n, which is geometric. Absolute value of r is equal to 1/3, which is less than 1. So sigma n equals 1 to infinity of bn converges. Now, if this converges, then I'm hoping, if I want to do the comparison test, that the an terms, which are positive, are smaller than the bn terms. And indeed they are, because that denominator is larger than that denominator. So we can say 0 is less than 1 over 2 plus 3 to the n, which is less than 1 over 3 to the n, which is the inequality in the direction we want. So by, for all n in z plus, let's just go with that, by the comparison test, we know that the series we were interested in, sigma n equals 1 to infinity of 1 over 2 plus 3 to the n, also converges. So the inequality went the right way, and the series of bn's converged.